Well, good afternoon, everyone. It is 2 o'clock in the middle of the Pacific. We will. We are getting on the way here. Just as a bit of housekeeping for our participants, if you need to go ahead and make any of the slides full screen, you'll see in the top right corner of here 4 buttons. Click on those; it will make your slide full screen. If you're coming back to watch this recording afterwards in the Adobe platform, you'll still be able to use that. Okay, that being said, the other thing we have to say is thank you to our underwriters. We've been very fortunate this year to receive a couple of underwriters that make it possible to have these events at very little or low cost. One is the WET Show, the Water and Wastewater Equipment Treatment and Transport folks. And I'm going to go ahead and put the web link into the chat window for you. Last we heard, the WET Show had been postponed from its normal date and put back to May 2021. We're all hopeful that by then perhaps Indianapolis will have got a handle on the break thing. That is the projected date for next year. And to Concrete Sealants, one of our board members, Sam Lyons, is the principal with Concrete Sealants, and we are very grateful for their financial and their professional support. So I'm just going to put this away down. And also, one of our other board members, Ben Keeley, is here, and he is going to introduce the speaker and give an overview for the series of education events that we have planned, and this being the first event. Take it away, Ben.
Thank you, Dendra. It's a pleasure this morning to welcome Dr. Mike Meng, who's going to be giving a presentation on his PhD research, which is anaerobic co-digestion to maximise resource recovery. And, you know, that sounds complicated or whatever, but what I love about Mike is where I saw him doing some of his research, he's the type of committed researcher who will get up at 3 o'clock in the morning on New Year's Eve to hop in a sludge pump out vac truck and go around to a series of pump stations and happily desludge his way into the new year. So Mike is 100% committed to his research, and the research of resource recovery is becoming that much more important. So it's renewable energy, it's nutrients, it's being able to protect the environment. So like here in Australia, through a large part of the state of Queensland, which Mike and I are both in at the moment, we worry an awful lot about nutrient discharges into the Great Barrier Reef. And the type of research that Mike is talking about not only produces renewable energy, nutrient harvesting, but it produces a better quality of water that is discharged into not only our freshwater streams, but our marine environment. So I hope that you'll enjoy this presentation. Mike's put an awful lot of work into it. He's had a very successful PhD project, and our next presentation will actually be about phosphorus recycling with a researcher who's currently in the middle of her PhD. So we'll have more about that up on our LinkedIn pages and various social things with once the dates are confirmed and everything's ready to go. So thank you for agreeing to do this webinar, and welcome, Mike.
Thank you very much, Ben, and thank you, everyone. Mike Meng here. Today, I'd like to talk about co-digestion. So it's a bit different, like Ben introduced. It's a bit different to wastewater treatment and some other types of wastewater and water treatment technologies. So it's more about solid waste management. In particular, I'd like to thank you very much, Dendra and Ben, for the introduction. Today, I'd like to shift the focus away from wastewater treatment and talk about another important, issue around solid waste management. So, in particular, I'd like to talk about anaerobic co-digestion as a way to optimize resource recovery potential from different types of feedstocks. So, I did a PhD on this topic. I currently work as a resource recovery engineer here in Brisbane. So before the presentation, I'd like to thank my organisation and also Aris Water, especially Ben Hill, to make this happen, and Dendra for organising all the event and make this happen, and of course my home university, University of Queensland, for supporting my research and allowing me to present all the results. We live in a world filled with different types of organic feedstocks or substrates or wastes. So they are problems, and at the same time, they represent different opportunities for resource recovery. So just to show a few pictures of what they're like. So we've got high-strength liquid organic waste from the beverage industries, and we have sewage sludge, that's a byproduct from wastewater treatment processes. And this is something each wastewater treatment plant has to deal with, because by treating the wastewater, we generate a sludge problem that has to be dealt with. And also fat, oil, and grease, typically from the grease trap, normally food waste in origin, is problematic. It can cause issues to the sewer. It has large energy potential in it that can be recovered for beneficial reuse. And we're all familiar with solid food waste and green wastes. So they exist in large volumes and different types in our life. And here in Queensland, we've got a lot of abattoir waste from slaughtering cows, and we've got a piggery waste as well. So these wastes are all different. They all make their own in terms of composition and quantity. And we need to do something about it. So importantly, to deal with the organic wastes, we need to stabilize them, because otherwise it will cause a lot of environmental issues and they won't be used as a useful product. Currently in Australia, according to the National Waste Report, there is about 14 million tonnes of organic waste generated each year, and 50% of the organic waste actually end up in a landfill. And interestingly, out of the 14 million tonnes of organic waste, 50% is food waste and garden organics. Like the previous slide showed, these wastes are really diverse in quantity and quality. Many technologies exist to stabilize or treat the organic wastes. High rate anaerobic digestion, aerobic digestion, lime stabilization, conventional anaerobic digestion, composting, just to name a few. But out of these technologies, anaerobic digestion and composting are typical. Anaerobic digestion is our focus of this talk, and this is something I've done a lot of research on. It is compared to composting, it is a more controlled engineering process because of the need to capture the renewable energy and the need for dealing with the downstream digested material. But AD is preferred at a scale. It's not always beneficial financially as a stabilization technology to deal with some kind of waste. But this is when co-digestion comes in to help, because for AD scenarios where the in-house digestion is not justified financially, we can bring in additional feedstock to generate more biogas energy and generate more useful downstream digested material to make the AD more attractive financially and also environmentally. So like I said, renewable energy capture is a key feature of AD, but composting at the moment in Southeast Queensland is generally cheaper and is a default option for stabilizing many types of waste, such as fat, oil, and grease, and food waste. Some green waste mingled up with food waste also goes to composters. But what I'd like to mention is neither technologies solve emerging contaminant issues such as PFAS and microplastics on its own. What this means is with the looming change in end-of-waste coal here in Australia, we might have to come up with a combination of technologies that can deal with the PFAS and microplastic issues. So what I'm saying is these technologies need to be integrated into some of the treatment chain to enable the best treatment outcomes. In terms of anaerobic digestions, different wastes have different degradation properties. Normally characteristic of the gas potential and the degradation speed during an anaerobic digestion process. They are all kind of co-digestion feedstock candidates, and we need to design co-digestion mixtures to enable the best outcome possible during the digestion process. Here, I just want to briefly introduce what anaerobic digestion is and co-digestion. So anaerobic digestion is basically a microbial process. As the image shown to the right, colorful microbes in the image captured. For the sake of this presentation, I won't go into too much detail into what each of the type of the bacterial archaea are doing in anaerobic digestion. Instead, I just want to categorize them into bacteria and archaea. So they are responsible for different metabolic steps in anaerobic digestion. So in a digestion process, there are four typical anaerobic metabolic steps: hydrolysis, acetogenesis, or interchangeably fermentation, acetogenesis, which converts organic acids into acetate, and which can then be used by archaea or methanogens to be converted to methane gas. So biogas is the end product of an anaerobic digestion process, but it starts from a complex composite feedstock or substrate and goes through a series of these metabolic processes to produce the end product. So what co-digestion, as the name suggests, is a simultaneous treatment of two or more feedstocks in one centralized digestion facility. And the impact of adding an additional feedstock to a digestion process is increased organic loading rate of a process. And by doing that, when we add additional feedstock to a digestion process, if the microbial capacity of the system is fixed, the microbes have to work harder to process the waste to produce methane. And what this also means is if we add too much of the feedstock without doing co-digestion mixture design, we might overload the system. Another impact of adding additional feedstock to a digestion process is it tends to reduce the sludge retention time of a process. If we reduce it to a level where it's below the critical SRT of the system to handle to properly stabilize the feedstock, it might have a negative impact on the microbial process and cause washout of the microbes as well. So yeah, this is an overview of the digestion and co-digestion process. So I guess the key goal of feedstock mixture design, anaerobic digestion, co-digestion, are strategic selection of different types of waste. And also sometimes when we have limited feedstock type available, because of availability issue of the feedstock, we need to know, the optimal volume of that particular feedstock we can add to the process in order not to overload the system. I guess the biggest advantage of co-digestion is to leverage existing infrastructure capacity of a digestion system, enhance the biogas production, which can be utilized in different ways, such as generating electricity and heat, which is a typical practice in Australia. And also there is green energy incentives in many parts of the world to actually use the biogas for higher value rather than just electricity. So I guess the goal from the process perspective is to minimize biological inhibition risk by adding various amounts of feedstock to an existing digestion process. The goal here is to minimize additional solids production out of the digestion process. It also needs to minimize downstream nutrient impact. But at the same time, through cold digestion, we want to maximize biosolids reuse options, which is a big driver for many of the utilities here in Australia to do cold digestion. I'll give you the example a bit later on how we do it here at the utilities. Like I said before, the dynamic nature of the feedstocks can be demonstrated in two aspects. One is the digestion property. The other aspect is the feedstock availability and the variability in composition. In terms of digestion property, as a bar chart shows, there are two main aspects. One is the biogas potential, the other one is digestion speed. Different types of waste have different gas potentials. Here you can see what the red bars show for different types of waste. The gas potential can be quite different. In terms of digestion speed, if we have a fixed volume of digester on site, we want to make sure the digestion speed of a feedstock is quick enough so we can achieve enough stabilization during the process. But they are very, very different from feedstock to feedstock. We definitely need to capture that dynamic nature of the substrate to make sure it's compatible with the existing operation. To the right, I showed an example of the EPA mapping tool, which kind of pinpoints where the organic wastes are near a central waste treatment facility. The waste can be spread across quite a wide range of geographic locations, and sometimes the ease of getting the substrate and transport can determine the ultimate feasibility of a cold digestion project. I guess what I'm saying is the substrate that ends up being selected is not necessarily the best substrate you can think of. It's normally the geographic factors that determine what actually got to the plant. And of course, seasonality is a big thing in feedstock selection, because different seasons we have different compositions from, say, food waste. And if that food waste is stored in some sort of way and not transported to the plant in a timely manner, it might cause a change in the feedstock composition and then change the digestion performance of that particular feedstock as well. So these are all the factors we need to consider in a cold digestion mixture design process. Here, the diagram might look a bit complicated, but it shows the feedstock design kind of method. I categorize the method into 4 key areas. So first is the substrate property management, where we try to understand what feedstock is. We normally do that by physical characterization. We want to measure the particle size, we want to measure how flowable the substrate is, if it's compatible with the existing operation. And we also want to quantify the chemical compositions in that feedstock. And in particular, we want to see if we can get decent amount of biogas out of the waste. And secondly, through the previous screening in step 1, we want to do cold digestion mixture design, because cold digestion mixture is always involved in adding an additional stream to the baseline substrate feed, which means we design a mixture to enable the optimal digestion process. So that's a consideration. That's where my PhD research was focused on, and we'll talk about it in more detail later. And in the digestion process, what essentially happens is the designed cold digestion feedstock mixture gets destroyed and form biogas, which is the product we want. And whatever is not destroyed will be washed out of the system and be part of the downstream solids handling process and nutrient handling process. And importantly, the degradable fraction of the waste is really important because the non-degradable AD, anaerobic digestion, is a biological process. Whatever portion that is non-degradable will end up in the biosolid stream as well. Biomethane potential testing is an effective way that's widely used to quantify the biogas potential of a waste. So it occurs in various sizes of sealed bottles, as the picture is shown on the top. In terms of what we add to a BMP test, the graph below shows the content of a BMP test. Normally, we introduce a mass of inoculum or microbes to do the job in a BMP test. And then, depending on the ratio we want, we add a certain mass of sample. We might need to dilute it by adding a bit of water, leaving the head space for gas sampling. So what we do in a BMP test is we periodically take a biogas sample out of the head space and run it through the gas analyzer to tell us the biogas composition during and development during the test. From the BMP test, we hope we can get graphs as shown to the right. The graphs show the BMP curves from different types of waste. Again, they look very different. I just want to kind of introduce a couple of examples from here. So, for example, the top graph, the blue line shows the CCA, which is the beverage waste, liquid beverage waste BMP curve. It's basically a first order curve that has a really fast digestion rate in the first few days, and then peak really early, and then tends to stabilize towards the end of the test. Whereas if we see a very different one, which is grease waste, the purple line, it seems there was a lag in the beginning of the test, and then it takes off after a few days, and then plateaued towards the end of the test. The reason for this behavior is when we supply a mass of the feedstock to a BMP test, the inoculum or the microbes in the test has to adapt to the waste type. And if we added too much, or if the waste is not welcomed by the microbes, they tend to take the time to adapt and then produce gas after the initial adaptation period. So the graph down the bottom here shows similar curves, but for different waste types. But all these kind of BMP curves show these wastes are so different, and they have different digestion speed as a slope of the curves show. They all plateaued at different gas potential. So again, we need a matrix to design co-digestion mixture to make sure we can get the best out of each different type of the feedstock. I guess one matrix we look at is substrate macro compositions. So substrate macro compositions are the carbohydrates, proteins, and lipid compositions in the waste. So different wastes are made of different portions of these macro compositions. They digest very differently in AD processes. For example, carbohydrates is metabolized during the AD process and forming organic acids quite quickly. And if we add too much of a carbohydrate in the digestion process, it tends to acidify the digestion process. Whereas for protein, during the protein digestion, it releases a free ammonia, which is a known toxic material to anaerobic microbes. And too much proteins to a digestion process can cause what we call a free ammonia inhibition, and it can toxicate the microbes by penetrating into the membrane cells and make them stop working. Lipids is another important composition in waste. As well as forming organic acids during lipid digestion, it also forms something called long-chain fatty acids. It tends to be sticky onto the membrane cell wall of the microbes and inhibit the mass transfer during the digestion process. But all these different macro compositions carbohydrates, protein, and lipids, give us a good simplified matrix to study anaerobic cold digestion processes because it's less complicated than different waste types, food waste, fog, green waste, which are made up of these different portions of these compositions. In terms of how each of the macro composition behave in a BMP test, here is a graph. So as we can see, the sewage sludge, which is the byproduct of a wastewater treatment process, has a moderate biogas production in a BMP test. Carbohydrate seems to be a little bit less than the sewage sludge in terms of the biogas production. Protein actually on its own can produce more biogas than sewage sludge, and it tends to digest faster, as shown by the slope of the curve, steeper than the red or the sewage sludge curve. But lipid is a really dense energy dense material that can give us a really decent amount of biogas production in the BMP test. But again, the goal here is quantify, if we have a complex waste added to sewage sludge, what will happen, because it's made up of a different mix of lipid, protein, carbohydrate. And the limitation of a BMP test is that it is a shock load test. As I said before, it's just we add a certain mass of substrate into a bottle. Whatever we add will sit in the bottle and has to be processed by the mass of the inoculum or the microbes in the bottle. If we add too much, the microbes have no choice but to take the time to adapt and process it to produce biogas. But whereas if we look at a typical anaerobic digestion process, it's continuous, which means there is addition of substrate to process, and simultaneously we've got a stream that's coming out to maintain the digestion volume. So a process being continuous also means it has washout and a growth of microbes during the process. So that's a more representative picture of a digestion process. And because of this reason, a BMP test is normally conservative estimate of a waste material in terms of digestion behavior, but it can be done in a quite cost-effective manner. And also, as you can see here, we finish a test in a month, whereas in a continuous digestion process, the 30-day period is normally an acclimatization period where it tends to stabilize the performance before we can get good data. So it's more time consuming. But once we do it, the continuous digesters can give us a more holistic view of a digestion process. So a continuous digestion trial is definitely a big part of my PhD. Here the picture shows the toys I had fun with for 650 days during my PhD. I ran this lab scale bench scale digesters for 650 days, 4 of them. So there was one sludge digester and 3 cold digestion digesters. In a cold digestion digesters, I had the same amount of sludge substrate, and in addition to the sludge substrate, I added controlled amount of either carbohydrate, protein, or lipid to be used as a matrix of the waste compositions. So the goal here is to progressive overload the system to find a maximum loading rate. So for industry, it's really important to know how much of each of the feedstock we can add. Is there a sweet spot in a process where we know how much we add to maximize the profit and digestion benefit in various ways? And also from this experiment, I wanted to quantify the process impact of different macro compositions, namely carbohydrate, protein, and lipids. A big goal of this trial was also to inform industry applications. We were working with water utilities and meat industries here in Australia to tell them, what feedstock would be the best type and how much to add to enable benefit. It's a CSTR, or continuous tank digester operation, which means the digestion process went on and not stopping. I feed a certain amount a day and draw out a certain amount a day to maintain the volume in the digestion process. Just to give you guys some specific numbers of loading rate, you might be interested in how much I've added. So in engineering terms, organic loading rate is a way to quantify how much COD you would add to a digestion process. It's also used in wastewater treatment. So in a baseline or the controlled sludge digester, I maintain the baseline to be 2.3. That's a kilogram COD per cubic meter per day. So that's a typical number in conventional anaerobic digester. For the cold digestion processes, I increase the baseline organic loading rate by 50%, 100%, and 125% through adding a cold substrate. So the cold substrates were added in addition to the baseline sludge load to achieve a higher loading rate. But I ran each of the loading rate for a decent amount of time to first of all enable microbial adaptation, and second of all to generate convincing data sets to show this is the case. And here I want to show some of the digester performance curves I generated from the continuous digester experiment. It might look a little bit complicated to you, but essentially what I want you guys to focus on is the matrix I use for measuring digester performance. The top graph is a daily methane production from each digester, and along with that, two key parameters I measured as a digester performance indicators were volatile solids destruction, that's a typical parameter we look at in anaerobic digesters, and COD removal. So through volatile solids destruction and COD removal, we achieve biogas production. And here, sludge only is in red, carbohydrates is green, and protein process is purple, and blue is a lipid. And as you can see, the sludge digesters perform quite stably throughout the experiment because I never changed the amount of sludge added to the process. But if you look at a very different curve, such as the protein co-digestion process, as I increase the loading rate by 50%, in addition to the sludge, it caused instability, demonstrated by a dip in the biogas production. But interestingly, the microbes could adapt, and the biogas production picked back up and tended to stabilize towards the end of the operating period. But as I added more substrate at a higher loading rate, the biogas didn't actually increase significantly, but it didn't decrease much either, unless I added even more to try to overload the process. That's where more instability occurred, and the biogas production will destabilize a bit more. On the contrary, the lipid co-digestion process performed really well, but there was an initial adaptation period where it was quite close to the other co-digestion processes, but as I tended to overload the process, and it gave the microbes enough time to adapt to the process, and the biogas increased gradually. And the biggest biogas benefit was realized at the highest loading rate. And if you look at the axis where it showed the time series of the experiment, it actually took me 500 days to see a decent amount of biogas produced from the lipid process. This is interesting to me because it means, the microbes are really amazing. They were magic. But the anaerobic process, it might respond really slow to additional load of the substrate. We need to give them time to adapt to that. But once adapted, we can realize a lot of benefit in biogas production. I think to better explain that, I did some BMP batch testing on microbial acclimatization of lipid. So the graph to the left showed the fat oil increase dose without acclimatization of microbes. So what I did here was collected the biomass that was not adapted to any lipid and added fat on oil and grease to progressively increase loading rate and try to see how the test behaves at these loading rates. And we can see, although it produced more gas at higher loading rate, there is a pathway to it. There was a significant lag as loading rate became higher. Whereas if you look at the curve to the right, where I acclimatized the microbes in a continuous lipid process and then collected the biomass then to do co-digestion tests with fat, oil, and grease. First of all, we can load the system higher, and as the curves showed, there was no significant delay. So gas response was pretty much immediate, which was good because that's what we wanted. Because for a fixed volume of the digester, we want the digestion rate to be fast, and we wanted the digesters to really to be at a high efficiency to convert different types of substrate to biogas. And what I found here is acclimatization is key. I guess for any digester performance measure, stability is important. Three important parameters are pH and volatile fatty acids, or VFAs. VFAs are the intermediate product in a digestion process. It's a precursor for the methanogens or archaea to use to produce methane. So if the system produces too much VFAs, it's an indication of the digesters being unhappy. We try to avoid VFA accumulation in the process. Soluble COD here, it's basically VFAs plus a higher chain soluble carbon. So it, as a curves show, it follows the same pattern, but it's just more in concentration. Here is interesting. I want you to focus on the purple lines, which is the protein process. It really struggled because the process was really unstable as I added more protein to it. As you can see, when the loading rate was increased by adding protein, the pH was shifted towards above 8, which is a high value for anaerobic digestion. It's not an optimal value. Whereas if you look at other processes, it tends to be more stable and lower, around 7, low 7, well below 8. So yeah, so pH, the high pH from protein co-digestion meant during co-digestion of protein, it released a lot of free ammonia, which tended to increase the pH. But interestingly, the VFAs or the VFAs were picked when I added protein initially, and then the bugs took the time to adapt, and then it decreased significantly and really stable for the first period of the operation. But when I added more, the VFAs picked back up and increased gradually, indicating a really unhappy digester. And the more the loading rate, the more peak we saw in the protein co-digestion process. But again, the bugs could still adapt because, as you can see, in the highest loading rate, the digestible stability was not good. But still, if we kept running the digester this way, it could still be processed. The VFAs could still go down, but still the concentration might be high. But the microbial capacity could develop over time to process the VFAs. One thing I want to mention is also the downstream impacts from co-digestion process. So during coal digestion, the organic nitrogen in the substrate will be solubilized and produce total ammonium nitrogen. This total ammonium nitrogen will end up in a downstream processing for a large sewage treatment plant. It will be in a centrate stream, which returns back to the bioreactors for additional treatment. So that can incur additional treatment costs. At the same time, phosphorus is also something we need to watch out for, because in a lot of the BNR, biological nutrient plant, biological phosphorus removal is also important. We want to make sure we have knowledge over how much nutrient return to the back of the plant, which would otherwise cause issues. So from coal digestion, we tend to generate more biosolids. These biosolids can be from two sources. Any of the undigested material will be biosolids. And also, if the experiment is long-term, like I did during my PhD, we literally grow microbes, additional biomass in the system. I know in anaerobic digestion process, the microbes tend to grow more slowly than aerobic process, but still, with a long-term experiment, such as an experiment that goes for 650 days, the microbial growth would be significant. But here, I guess the key message is protein co-digestion generated a lot of total ammonium nitrogen in soluble form during that digestion process. And this is also a big reason why we saw the VFA peaks in the previous slide. See a lot of see the drift in pH being non-optimal during the process as well. So what I found here is protein co-digestion caused a lot of stability issues and downstream impacts, but I didn't see any negative impacts from lipid or carbohydrate co-digestion in a long-term experiment. So I guess another interesting finding is from the financial aspect. The feedstock financial analysis basically showed that the financial returns of adding a feedstock is not linear to the loading rates or the amount of feedstock added to it or the biogas production, because it's an co-digestion is an interactive process where we get process benefit in biogas. At the same time, it is a business as usual operation for many water utilities here in Queensland. What we need to deal with the additional biosolids downstream. We also need to treat the centrate nitrogen and phosphorus. So these are all the cost factors we need to factor in. And when we did that using like a typical Southeast Queensland values for the analysis, I used my process data collected from the experiment to do the analysis. I generate the bar charts shown on the top. Basically, it showed for carbohydrate process, it's not linear to the amount of carbohydrate added to the process, but it was not a significant decrease in financial values either. Whereas for the protein process, the more protein we added, the more downstream impact we got, and because of that, the financial impact was quite negative. For lipid process, it was interesting because when I added more lipid at 100% increase of the baseline organic loading rate, you see the financial numbers show a significant decrease, but it picked back up at high loading rate, and this is because of the microbial acclimatization to the feedstock, and a lot of biogas was generated towards the end of the experiment or at the highest organic loading rate of the experiment. So that's why the financial returns were the highest for this loading rate. So during my research, I used compositionally controlled material added to complex sewage sludge. So in the system, I had a pure lipid source, pure protein source, a carbohydrate source added to sewage sludge collected from a biological nutrient removal treatment plant. But these studies needed to be validated through a full-scale co-digestion trial to see if the full-scale process would behave the same way. And here we chose a piggery in the regional area of Queensland, which ran CSTR-style reactors for the pig manure treatment process. And cattle paunch was selected as a co-substrate to be tested here because of local availability. Like I said in the previous slide, it was only available at the time of the trial, and logistically it makes sense to transport that material to the plant rather than sourcing better material for the trial. But here, the paunch is a stomach content from animal processing. It represents a carbohydrate source with high fibers, and really you can see the photo showed it's very solid. It represented a lot of material handling challenges, and it has a pretty poor biological characteristic, which will show in the next slide. But in a trial, on a volumetric basis, we added 10 to 20 tons of paunch per day to 20 kiloliters of the pig manure to the process. So in terms of the feedstock mixture in the process, we did an analysis individually for both pig manure and solid cattle paunch. So pig manure, qualitatively, it had really moderate methane potential at lower temperature, which is a relevant operation condition in regional Queensland. It's typically not temperature controlled. So in winter, we tended to get pretty poor gas capture and production from pig manure. For solid cattle paunch, because it was high in fiber, not particularly known as a highly degradable product of paunch, and therefore the methane potential was also low. For pig manure, it has pretty high nitrogen content in it, and this means the biologic inhibition risk from this material is also high. But still, we chose cattle paunch to do the trial, first for availability reason, and second of all, in terms of composition, these two materials are quite complementary to each other. Pig manure featured high nitrogen, relatively low carbon, but cattle paunch is normally high carbon, low nitrogen, which can dilute the nitrogen and mitigate inhibition risk in the pig manure. And we did the trial. We increased the pig manure reactor loading rate by about 50% for adding paunch. And here I want to show some of the results from the full-scale experiment. So here I want you to focus on the blue line is the average from the baseline production of the pig manure. Through addition of cattle paunch, we increased the methane production by about 80% to 100%, which is consistent with my previous research on carbohydrate-based experiment. And there was a significant decrease in methane production during the days when we didn't add paunch, because we didn't get paunch samples during those days. And as you can see, when we didn't add paunch to the process, the methane production decreased clearly. When we added it back up, when we added it to the process again, the methane production picked back up. To the next slide, I want to talk about digester foaming and loading rate. So during my research, I didn't see any foaming issues from the micro composition long-term experiment, because I did a long-term experiment with a fixed loading rate. I controlled the loading very carefully, and also those co-substrates, carbohydrate, protein, fats, were compositionally controlled. So it didn't represent a complex substrate mixture, whereas digestive foaming tends to happen at a high loading rate when we digest a complex feedstock. it's a microbial problem. Many people think it has little to do with the microbial, it's just a foam on the top of the digester, but it's the root cause of digester foaming is microbial. It can be caused by filamentous bacteria. It can be caused by unhappy methanogens in the process that stop producing gas and tended to producing funny foams that gets carried to the top of the digester by biogas. So this process, so foaming can be worsened by process conditions such as low temperature and really inconsistent loading rate, which tends to form surfactant. So VFAs is a typical surfactant. If we've got VFAs in the process, we tend to sour the digester first of all, and also if the loading rate is inconsistent with complex substrate mixture, then it tends to form the digester. So here, saying that the feedstock was complex and meant I used a combination of the meat industry feedstocks. I used the lights generated from the slaughterhouse, paunch, the DAF sludge from their meat processing process, and the red screen, which is basically red meat residues. So I mixed these things up on a volumetric basis to form a mixture, and I fed the digesters a mixture of these. So a picture of the mixture is shown in the photo, not really pleasant, but that's what I do. So here I want to show some photos as well as some performance data of the foaming digesters. So I ran two of the digesters, which were duplicating each other. And as you can see on the top graph, this is how I controlled organic loading rate. I didn't really control it, I let it fluctuate it. So it fluctuated quite a bit in the beginning of the trial, and then I add a lot more to the process, which tends to increase organic loading rate really, really suddenly. So what this gives me was a gradual development of the following issues. As you can see to the left, if you see week one, I started seeing foam on the top of the digester, but I kept the mixing going, I kept feeding, but the loading rate was not well controlled. Then the foaming has started to really develop. And 4 weeks in, the foam was literally 20% of the digester loading of the content. And at 8 weeks in, I had to open up the digester because it caused mixing issues, and it caused a lot of operational issues. I couldn't carry on. I had to open up the digester to deal with the foam. But one of the aims of the trial was to see how severe the foam could become. Then so in a way, I achieved that outcome. But as you can see, if you see the loading rate all over the place in conjunction with the VFA profile in the top graph, you see when I really suddenly increased that loading rate, I saw a peak of the VFAs, which, like I said, is a surfactant that can worsen the foaming issues, and foaming already developed in the system, and the VFAs make it worse. But at the same time, if you look at the methane production from the system, it's not good, but the methane production didn't cease, which means you might still get a bit of a benefit of biogas production from foaming digesters, but it's not optimal. So foaming issues is something we need to deal with. So overall, this concludes my learnings from research. So basically from my experiment and validation studies, I found that lipid or fat was the most beneficial feedstock. Carbohydrate system also functioned quite well, and that was validated through a paunch co-digestion trial. What I also found, and this is probably the most important finding from a PhD, is acclimatization of microbes means co-digestion capacity increases over time. So before my experiment, before the PhD research, I read papers about loading limits and all sorts of textbooks about how much we can add a particular feedstock to a sludge digester, for example. So textbook numbers are generally conservative, because not saying textbook numbers are wrong, have a lot of respect for textbook numbers, but they do not consider this acclimatization process in a co-digestion or the digestion system, which is really key. And what I found was if a co-digestion capacity microbially is developed microbially, it means we can process more and more feedstock over time and increase the capacity of the biological system in the long run. So that's really important. There are two typical measures for digestion capacity. One is obviously the slug retention time, and it's normally recommended that 20 days or above are necessary for digesting complex substrate, and I believe so. But once the acclimatization has developed more biological capacity, we can push the digesters harder, which means we can lower the digestion retention time by pushing more material in. But we really need to develop that capacity first this time. And similarly, when we add a co-substrate to the process, we increase organic loading rate of the process. So to start with, I would recommend 50% increase of the conventional 80 digest loading rate would be sensible, because that way we give the microbes a chance to know what's coming, and they can know more about what they need to do to process the waste. Basically, they're like humans. From the co-digestion of protein, I found it was high risk because of a free ammonia inhibition. It also caused a lot of downstream impacts, such as additional biosolids, nitrogen and phosphorus loss in a soluble form. Like I said in the previous slide, foaming is a process challenge when digesting complex feedstock at a high loading rate. So to combat that, we should try to keep the loading rate consistent and control it carefully and ramp it up rather than getting it all over the shop. But once it occurs, it can be solved just by adding antifoams. That's what we do at a full-scale plant. The second part of the presentation, I want to show us a case study at Lush Pond Sewage Treatment Plant, STP. This is a plant where I spent most time on now. So I work at a plant as a resource recovery engineer. Just a bit of an overview of the plant. It's the second largest in Australia, 750k equivalent population. It treats about 130 litres per day annual dry weather flow. So the mainstream process, as you can see, it runs a series of bioreactors in 5-stage identical bionutrient removal plant. And at the plant, we are actually currently building a side stream animals that treats the centrate nitrogen from the digest state from the centrate through our dewatering system. I like digesters, so on site we've got 6 conventional anaerobic digesters. As you can see, the round stuff to the left. You might count 8. There are 6 sealed anaerobic conventional digesters and 2 are storage digesters, which are open, so exposed to air. So we run the sludge through the 6 conventional digesters, and digested material coming out of the digesters are kept in the 2 storage digesters before feeding the centrifuge for dewatering. So at the moment, the plant is 70% energy self-sufficient just from the sewage sludge alone, because we treat a combination of primary sludge and waste activated sludge that's generated from the bioreactors. And because we've got primary sludge, that increases the energy potential of the sludge mixture, and we get a decent amount of gas, biogas produced only from the native sludge. Biosolids disposal is the largest operating cost for us. The process generates 140 watt tons at 20% solids, at 20% dryness through the centrifuge process. It has been a significant cost for years, so we've spent more than $3 million Australian dollars per year to truck the biosolids for beneficiary reuse. Here we do have a cold digestion civil facility at Lecture Point. The picture shows what it looks like. It's a concrete tank that has an unloading system that consists of a strainer filtration system that prevents a rag and rocks and any unpleasant material from coming through. It protects the pump, but after the material goes through the filtration system, it gets unloaded by the centrifugal pump, feeding the what we call the craft tank. We call it craft tank. It's a small concrete tank in the background. You can see here. And without the material being kept in the tank, we feed the digesters straight away in a shock loading format. You might think, why don't we stabilize or let the material sit in the tank for a bit before feeding the digesters? There's practical reasons. One is older. The other one is the tank is actually not big enough. It's 10 cubes. So one truckload is normally 20 cubic meters or kiloliters. So yeah, we need to start feeding the digesters the moment we start feeding the unloading tank. So in terms of what we cold digest on site, we process about 60 kiloliters of liquid waste in addition to our mixed sewage sludge. And from cold digestion, the biogas production contributes to about 10% of total biogas produced on site. And like I said, the current unloading system has limited balancing capacity, which means the digesters have to be shock loaded, which can cause process risk. It can happen, but we need to optimize feeding strategies to make sure, you know, the feedstock mixtures can be trickled in to produce gas when we need it the most. Fat oil and grease is a really energy dense material. We know it's a good material, and we are really keen to do it at full scale. And what we've done so far is we've done some optimization around the fog analysis. We've done some trials at a full scale as well. But we're currently analysing it a bit more before we sign a commercial contract with the customer to take the fog base. Yeah, I want to talk about the biogas value and the biosolids management issues that we face. So these are the two practical issues we face at a full scale. You know, biogas is valued differently from country to country. Even in Australia, there will be a local difference in terms of how biogas is used, is valued. So we know we've done analysis on different feedstocks and different volumes and how much biogas the feedstock can produce. That's quite clear to us. And for example, we know that if you look at the pie chart, 3% of the fog volume, the market available fog volume, will give us 12% of the increase in the biogas, which is something we really like, but we really need to unlock our biogas value issues, because we have two kind of areas that stop the biogas issues being biogas values being increased. One is we have quite cheap electricity on site. We have a quite cheap electricity deal from our energy retailers. So to convert more biogas to electricity actually costs more than if we buy it from the retailer. A second issue is our cogeneration unit is at capacity at the moment. We try to bring in a larger cogeneration unit to be able to produce more electricity and increase the biogas processing capacity. There are also some higher value gas use options being considered. We want to use the biogas to dry our biosolids and achieve better dryness, which means less biosolids disposable volumes, and we can run the digesters hotter by using the waste heat from the cogeneration unit as well. So these are options that are being considered as part of the resource recovery program we are initiating. At the same time, like I said before, shock loading is not ideal. It can happen, but there's a limit to it. We want to try to pace the addition of feedstock material to our sludge line so we can realize that energy benefit throughout the day rather than have an energy surge when we don't really need it. Here in Australia, we have a strong push for renewable energy as well. So hydrogen is increasingly popular here in Australia. We are supporting policies that are coming out, in the next couple of years, and different parts of Australia are looking at different market options for hydrogen. There is also green energy sales potential for the biogas generated. Here, it's more like a partnership opportunity with the energy retailers to take a lot of biogas from the large treatment plants such as Lunch Point and produce electricity from a green energy source. Here, the bar chart down the bottom shows the feedstock treatment costs going through the coal digestion model I generated for urban utilities. The grey bars show, the biosolids handling is a big cost factor. Like I said before, it's really, really expensive to get rid of the biosolids, and we knew by adding more feedstock, there will be undigested material to an extent, adding to that biosolids volume we have to deal with. But the goal is to really, to minimize the grey bar in the chart. And we'll talk more about the biosolids handling in the next slide. So biosolids management is key to our full-scale coal digestion because we realize coal digestion is a really interactive process. And currently we ran centrifuges to dry the digested material from the storage digesters. We ran centrifuges quite hard to achieve about 20% dryness at 140 watt tons per day. And this corresponds to 3 million of trucking costs per year. We don't want that. We want to make the biosolids drier and less volume. So we've got a kind of project going on that looks at utilizing agricultural types of stockpile drying, which takes the dewatered cake from the centrifuge process and spray on the drying bed and do a bit of wind blowing and let the sun do the job. And by doing that, we estimated, we can significantly reduce the biosolids volume that's produced from our process, and that unlocks coal digestion potential significantly as well. That's not the end product from the drying bed. We're also looking at using the 70% or more dried biosolids for a further biosolids handling process, which is pelletization. So we've got a pelletization plant at Lunch Point. So pelletization processes, pelletization is a process that utilizes natural energy source such as solar energy to do the drying with the aid of chemicals to bind the material. So from the pelletization, we get pellets or the balls. You can see the middle picture to the right. So these pellets have two values, typical values. One is the calorific values, still very dense in energy, which can be utilized by, say, a local power station, like the bottom picture shows. It also has a decent amount of nutrient in it, so slow released nutrients in the pellets can be used as a fertilizer for agricultural lands and all sorts of different agricultural-based purposes. But through this burning process with the power station, the attractive aspect of that is it eliminates the PFAS and microplastic issues, which can be regulated soon here in Queensland. One existing project we are doing is a fault dosing optimization project. So it's important, as previously discussed, it's a shock loading versus distributed feeding project. So the bar chart, the charts to the left show the two feeding strategies of fog material to our digesters. As you can see, we set the limit indicated by the red line here. If it takes 3 truckloads of fog to each point, and if we feed the material as is through our existing tank, it means it will exceed the feeding limit because there will be too much fog in too short a period of time, which might cause biological inhibition issues and really compromise the biogas production. That's not what we want. What we more want is the graph down at the bottom, where we optimize that energy profile throughout the day by dosing the fog. Really, we spread the volume out throughout the day and dose it bit by bit to when the plant needs it the most. But to do that, we need to integrate larger volume of balancing tank, as shown in the photo here, to add to the process. So that way we achieve a more sophisticated balancing system that can do the job. I do a lot of co-digestion on site, which means a lot of material handling issues and a lot of substrate quality management on a day-to-day basis. So we've got a big digester to support anaerobic digestion. We've got large digesters that have a lot of unutilized capacity. We want to fill them up as much as possible, but substrate quality management is really important. As you can see, truckloads come in every day. We need to manage truck movement on a daily basis, and what's coming out of the truck can be really unpleasant day to day as well, as the bottom pictures show. So yeah, so there's a lot of material handling for our operators, for myself, and for a lot of and there's a lot of communication with the waste management companies and transportation companies as well, to make sure the product can be delivered on time with the right quality and quantity. We've got a waste acceptance criteria that help us select the best quality of the substrate, but still there is a lot of inconsistency in the quality of the substrate day to day. One way to control substrate quality is development of a substrate model. I developed this model with a software engineer. So basically, we did spreadsheets where we modeled all the different substrate mixing ratios and defined our digestion capacity. And at the same time, we quantified all the downstream impacts from doing different types of co-digestion activities. What the software engineer then does was to present the calculated results in a more user-friendly format. We use Python to do a bit of coding, develop a more user-friendly interface to allow us to make co-digestion decisions more quickly. Here is just an example of the interface with the visualizers where the customers are. It's a bit like the mapping tool I showed previously, as the rest of the world is using. It also tells us the cost and benefit of bringing in such substrates. If we click on a particular box on the map, it will pop up automatically what the cost and benefit looks like. It also defines our digest capacity instantaneously if we click in and out of the box. And to the right, it also shows interaction with different processes on site. So it needs to go through co-digestion infrastructure where we optimize the feeding methods, and in the digesters, the hope is to produce enhanced biogas, which can be utilized in some way. Here on site, we use cogeneration to produce electricity on site. Whatever the cogeneration unit can't handle will be flared. And here, ERR means Expanded Resource Recovery. This is our current resource recovery program. And we are looking at diverting some of the cogeneration biogas into the ERR option. Like I said, different options being considered for biogas utilization. Through dewatering, it generates biosolids. We've got BAU activities to truck it off site for beneficial use on land. For the expanded resource recovery, we look at drying it a bit further and utilize it for palletization and a further processing process that eliminates emerging contaminant issues. The centrate will return to the inlet works. If we've got so Anammox process is being built to take out the majority of the central nitrogen load in a more cost-effective manner. Whatever the Anammox is not treating, it will be returned to the inlet works for mainstream biological treatment. And in the extended resource recovery program, we also look at using stripping technologies to deal with more elevated ammonia levels in the centrate to enable recovery rather than just treatment. We realize the recovered nitrogen might have better fertilizer value in the market. This is an ongoing project. Here, just to summarize our pathways in coal digestion in Queensland too, it's driven by both internal and external factors. So here in Queensland, we now have the landfill levy that introduces a higher fee for waste going to landfill. This is good news for coal digestion because it's financially it makes more sense for redirecting the waste away from landfill for beneficial use, which is a good environmental outcome as well. But to do that, we are trying to debottleneck that biosolids issues and emerging contaminant issues to allow us to do more and more coal digestion. And renewable energy is a big one as well. There are a lot of environmental drivers for us to do that. But if you look at the diagram here, we have to deal with that sludge every day. That's our business as usual practice. Coal digestion liquid is full on at the moment. We digest a lot of liquids, and we realize liquid digestion makes a lot of sense operationally because liquid is easier to handle than things like fat oil grids and solid food waste. But we're looking at unlocking more capacity of coal digestion through enabling biogas value and the biosolids management. So by doing that, we really want to do more fat oil grids, solid food waste, coal digestion. There are trials and optimization projects going on. So here I want to say that coal digestion should be considered in a broader resource recovery scheme. Utilities, we want to turn the treatment plant into resource recovery centres. We have a lot of aspirations to do this, but at the same time, it's really important to know the interaction of coal digestion with all these downstream products as discussed in the presentation. That involves a lot of collaboration with municipality, with neighbouring utilities, and the biogas generated needs to go to the industry in some way, instead of just relying on cogeneration to generate electricity on site. Agriculture is an important factor for our coal digestion journey and resource recovery in general as well, because all the digesting material treated further in some way is hopefully can be used by agricultural sector for beneficial reuse. But here, I guess, without going into too much detail of each of these activities, what I want to say is coal digestion is really interactive. It needs to be considered in a more holistic view. And this is also my point for my concluding slide, the first point. It's highly interactive. And at different plants, there might be different process bottlenecks. It can be simple things like, the pumps and the filters being not compatible or too much material handling, or it can be a larger issue such as the biosolids issues we face. It's not necessarily a process capacity issue. We might have the largest digester in the world, but it doesn't mean we can put in a lot of material for coal digestion simply because the downstream process might not make sense. And to do that, feedstock quality control through acceptance criteria is really important. In our criteria, we have the typical chemical compositions such as PS, VS, chemical oxygen demand, things like that. We also have heavy metals and emerging contaminants, which are really big issues moving forward. These things need to be addressed for coal digestion to be unlocked. And material handling is a big part of day-to-day operation. It's really important. And lastly, I want to say that water industry in Australia is transitioning into the full spectrum of resource recovery with both internal and external drivers. So these are really important for us. It's more integrated. So wastewater treatment companies are not just treating wastewater. The job is broader than just getting the water clean and discharged to the receivable environment. It's about integrating more organic solid waste, especially for big utilities like urban utilities where I work now. So, yeah, that's the end of the presentation. I thank you very much for that. And lastly, I want to acknowledge again the input from ARIS, from the University of Queensland, and Wastewater Education, and urban utilities for the support of the presentation. Thank you very much, everyone.
Thank you very much, Mike.
Take it away, Ben. Do you see any questions coming in by text or by email?
Well, Ross is typing there, and while he's typing, Mike, did you use different types of antifoams in your foaming process? Because they can have the type of antifoam can have an influence as well.
Yeah. So we have foaming issues at one of the STPs through the Canby process. That's a Oxley Creek treatment plant. I don't know the specific type of antifoam we use, but it's just one type. What do you recommend, Ben?
Oh, it's not so much recommending anything, but different antifoams have different effects, and some antifoams themselves can be an energy source in these type of digestion, and others can inhibit. Yeah. So some of through a different project in a different industry, I've actually had to work with companies that have changed antifoams and they've upset processes. You know, they've swapped over to a better deal or whatever, and they thought they were just inhibiting foam, and it's actually had a impact on the treatment process. So because of that knowledge, when you're talking about the foaming and you're adding the anti-foam, I was just thinking, did you try different types and have a look at that?
No, we haven't tried different types, but it's a good point, Ben. It's probably worth trying. We haven't really tried different types.
Ross has asked a question there. Mike, down in the chat box.
Yep. What do you see? Thank you, Ross, for the question. I think to develop this in the industry, it's more integration. Because at the moment, an example to give you is here at Urban Utilities, we're trying to form partnership with waste management companies. And to be honest, at the moment, not everybody gets it because we still think, we're wastewater companies. Our core business is to treat wastewater. But now, because of the internal and external drivers, energy drivers, environmental drivers, we need to really form that partnership in a more integrated approach to enable more of this. I think the key is a partnership and integration. Thank you.
Yeah, that's a really important point. Do we have any other questions coming through? Ross is typing again. You must have really struggled at conferences where they only gave you 15, 20 minutes to talk, Mike.
Oh, sorry, I didn't even look at it.
Yeah, no, you're coming up right up to 11:30. You're channeling the spirit of Ted Gardner.
That's funny.
So, yes, he may watch the recording, so I'll expect an email or a dozen of them. Ross has asked another question there, Mike.
Yep. Good question, Ross. I think this microplastic issues, that's not what I have seen at our plant because we haven't done much of the co-digestion, the solid waste co-digestion. But what I do know is food waste will be a known source for that. I think the challenge here is what we do with the digested material. If we do a lot of co-digestion, it will bring a big change to the digest state coming out of the digestion process. That's what many other sewage treatment plants which do co-digestion have seen. But at the same time, to eliminate that microplastic issues, I would suggest have a downstream technology that can treat the microplastics, such as pyrolysis, is really important.
Mike, that was a really great slide that you had up there with the contaminants in there with plastic material and sludge and hair and various bits and pieces. How many fruit stickers were in that? Because wherever I scrape through that type of stuff, there's thousands upon thousands of fruit stickers off fruit.
Yeah. Yeah. Oh, we see. It's really hard to quantify. Actually, it's really day to day we see a lot of that thing. And on a bad day, I had to dispatch that for hours. Not necessarily me. Our operators had to work really hard to really solve that issues. Is that what you asked?
Yep.
Again?
Yeah.
Yeah. So I guess we do have waste acceptance criteria that says strictly no foreign matter, no rags, no rocks, no other things. But what we also found was, the waste transport companies, the trucks and the driver, depending on the day, it might have different things in it. They might just pick up a load and unload somewhere and go pick up another load. So there might be cross-contamination issues from that reason. But this is something really, it comes down to communication and really make the criteria stringent, I think.
Do you think that perhaps a price, if that it's an uncontaminated load, gets paid more, or it's cheaper to receive than one which has got a high amount of contamination in it, might drive those waste companies to ensure that their loads are a bit better managed?
Yeah, I think that's a good question, Ben. It depends on what contaminant we talk about. If it's just the contaminants that cause material handling issues, then it's manageable. It's just a matter of screening it out or control the feed in. It's not necessarily more expensive that way. It's just about comes down to criteria. If the contaminants you mean, in microplastics and PFAS or other chemically related contaminants, then it will involve a downstream technology to treat that, and then it will increase the fee to treat it. At the moment, our gate fee model consists of 4 parts. The receival facility, the biogas cleaning, and a downstream phosphorus and nitrogen, downstream nutrient and biosolids treatment cost. But it has not considered any contaminants in it. But we've got some thoughts on how to incorporate that depending on the technology we're going to use.
Yeah. Well, thanks once again. Is there any other questions coming through? We're at our 11:30 mark, which is where we said we'd go to. So, by the look of that, you had a fun-filled, 3 and a bit years of your PhD there, Mike.
Yeah, I had more than that.
Yeah. I have one.
I'm sure you discovered some interesting smells.
I have one last question.
That's it.
You said that you ran your tests for 650 days. Are those tests still ongoing, says the person who sent them?
No, I wish they were. I was really keen to stop it towards the end of it, and I dumped all the material down the drain.
Was there a tear, Mike?
Sorry, the sound didn't come through. What?
Was it an emotional tip down the drain? Were there tears?
I almost did. I almost cried, but it was happy tears as well. But Daniel, that was actually a good question. We actually thought about continuing the trial because, like I said in the presentation, there was good acclimatized bugs, microbes that were grown during the trial. It would be interesting to continue it on and test different materials with the acclimatized population, but we decided not to do it eventually.
Okay, ladies and gentlemen, are there any other questions? As they say, chat now or forever hold your comments. Not seeing any. Thank you so much, Mike. This is a big chunk of your life that was devoted to this. And I'm so sorry that you had to tip 650 days of it down the drain.
All good. Thank you very much, guys. Thank you, Dan. Thank you, Dendra, and thank you, everyone.
Just to let everyone know that the next event in the series is scheduled for November 10th, and it's another take on resource recovery, and this is a self-contained treatment unit for potable water reuse. We hear a lot about non-potable reuse options, but the idea of having a completely closed system is a challenge, and it would be interesting to see if these guys have pulled it off. So Ben has mentioned that the next event in this series for the Australia presenters deals with phosphorus recovery, and we will be seeing the date and registration for that shortly. That being said, thank you again to the wet underwriters and to Company Sealants and for Ben taking time out of his day to host and co-moderated today. But most of all, thank you, Mike, for giving us such a great overview of your PhD.
Thank you very much.
I'm going to stop the recording now, and thank you so much, everybody.
Thank you.